Okay, I think it is time to start. The next speaker is Jean-Philippe Bouchaud. I think that he is so famous that everybody knows him. Nevertheless, let me say a few words as an introduction. Jean-Philippe Bouchaud is professor at École Normale Supérieure in Paris and co-founder and chairman of Capital Fund Management. He has been active in the field of the dynamics of disordered systems like glassy and granular materials, where he has made outstanding contributions to many fundamental problems, including anomalous diffusion, aging phenomena, and jamming. He is member of the French Academy of Science. Jean-Philippe was one of the initiators of what is called today econophysics, and has been since then a leading personality of this new discipline, where the methods of physics, especially of statistical physics, is applied to problems of economics and finance. But unlike many others, he had the ability and the courage to start a company where the novel approach could immediately be tested. His initiative has brought its fruits. Capital Fund Management is a successful global asset management company where theory and practice complement each other. Jean-Philippe, the floor is yours.
Thank you, Janos. It's a very nice introduction, and I'm really happy to speak about these subjects these 2 hours to come. So I guess you see my screen?
Yes.
Yes, okay.
Great.
So I'm going to speak about applications of ideas of statistical physics to economics and finance. And so these 2 lectures will be about more or less the same subjects, but with different points of views. So the first lecture is collective effects, crises, and discontinuities. And it's going to be about a translation of the random field Ising model into the realm of economic systems. Although, of course, the random field Ising model is well known to physicists, it's less well known to social scientists. So the abstract of these 2 lectures is as follows. Financial and economic history is strewn with bubbles and crashes, booms and busts, crises and upheavals of all sorts. Understanding the origin of these events is arguably one of the most important problems in economic theory. And the point, as I'm going to insist, is that a lot of the economic models that are used to these days are mainly focused on what I would call normal fluctuations. I mean, small fluctuations around equilibrium. But then when it comes to bigger effects, a lot of these crises are kind of difficult to explain within the traditional context of economic models. So let me give you first a little review of some of these examples of discontinuity. So, for example, the crash of 1929, as it's probably well known, there's been many crashes in the history of financial markets, but one of the most acutely remembered one is the 1989 crash. There's one in 1987, and the point is that there's a huge discontinuity in prices, around 20% in a single day, and no very easy to identify cause of that discontinuity. So there's not a big macroeconomic shock that hits the system and that can explain what happens. So, for example, an example of exogenous shock that is well identified is the COVID 2020. Here, it is not the stock exchange; it's an index of confidence index, and then so you see it fluctuates due to external shocks, and then there's a big shock, which is COVID 2020, which leads to a huge drop in the confidence of households or of firms. So this is going to be a main theme. There are 2 types of big events, some that are easy to understand and identified clearly as an exogenous cause, but others that one will have to try to explain within another context, and this idea of endogenous fluctuations will come to the fore. Another example of confidence crash is what happened in 2008. So 2008, maybe you remember, there was this subprime crisis, and the subprime sector is actually a very small sector of the US economy, but still it managed to wreak havoc in the banking system. This red curve here is, I won't go into the detail of how it's defined, but it's essentially a measure of the mistrust between different actors in the banking sector. And so you see that as soon as early as July 2007, there's a rise of this trust index, and then when Lehman defaults, there's a huge increase of this thing. So of course, Lehman default is a big event, but in a way, it's still difficult to understand how a small problem like the subprime has been able to generate such a big crisis as the 2008 crisis. Other examples of discontinuities or rapid changes, I won't go into all of them. One which is very interesting, I won't have time to speak about it in details, but maybe you'll be interested to investigate this phenomenon. This is the correlation between the fluctuation of the stock market and the bond, US bond treasuries, for example, fluctuations. And if you believe economic theory, it should be a positive correlation. That is, when bond prices go up, stock market goes up, and vice versa. And the reason is that bonds vary inversely to rates. So when rates go down, it's supposed to be good for companies, and therefore prices should go up. But then in 1997, at the end of 1997, there's the so-called Asian crisis. And in a matter of days, this correlation that was staunchly positive for years has become negative and stayed negative. So this ends in 2003, but actually up to the COVID crisis, it remained negative. So there's a sudden change of polarity of this correlation that occurs very abruptly, a little bit like the inversion of the magnetic pole on the Earth, or the sudden reversal of magnetization in small magnets. This is another example of rapid phenomenon, which is the drop of birth rates in Europe in the late 60s, early 70s. And here are two examples, Germany and Portugal. Germany drops very quickly, Portugal much more smoothly, and I'll come back to that effect later. This is an experimental data curve that we constructed. This is another example on which I'll focus through the lens of the random field Ising model, which is how applauses end at the end of concerts. So I'm sure it's your experience too. In some cases, people keep clapping for a long time and the clapping goes down very smoothly. This is the red curve. But in some other cases, in particular in France, where people are very concerned not to continue clapping like idiots, you see a much sharper drop at the end of applauses. And it's possible to analyze these curves more quantitatively, and I'll come back to that, as I said, later. This is a completely different topic. This is mechanics. This is the way solids break when you pull on them. And as we all know, there are two types of way of fracture. One is called ductile. You start pulling and the object deforms and then drops. I mean, there's a precursor to the drop, which is in the stress strain curve, a slowdown of the increase of stress as the strain is increased, and then there's a failure point. But there's also another more dangerous, in a way, situation where there's no precursor. You pull on the sample, and then at one point, out of the blue, the system breaks, and this is called fragile. So this phenomenology of having smooth evolution versus sharp evolution is, of course, something that exists in physics as well. So coming to social phenomena, let me show a few of them, which are also quite striking. One is this which I've lived through in a way by crossing the bridge, the Pont des Arts in Paris every day going to work. And as you see, there are lovelocks on this Pont des Arts. And it was really fascinating to see that in a matter of a few weeks, the Pont des Arts had only a few, and then it was completely filled with these lovelocks, showing that people, of course, react to what others are doing, independently of whether it's rational or it makes sense to do those things. So this is the lovelocks. And of course, another well-known social phenomenon is called the Mexican wave, where people coordinate and create these moving waves that go around stadium. Of course, there are things that are much more serious, like riots and the propagation of riots that have been studied in the socio-economic literature, in particular by Granovetter, Schelling. And if I have time, I'll explain a little bit what French scientists have done about riots around Paris in 2005. So my screen won't, no, strange. So this is another type of measurements, which I think is quite interesting, and was promoted in particular by Didier Sornet in the context of book sales or YouTube views. So these are two examples of the trajectory of book sales as a function of time from Amazon. So in this case, what you see is an example of an exogenous shock, in the sense that maybe the author spoke on a radio program or on a TV program. So the number of books per day that are sold is around 10. And then suddenly it jumps to 100 or more. And then there's a slow decay of this number of sales. But in other cases, the profile is completely different. It seems that the peak is reached not in a discontinuous fashion, but progressively from the past, reaches a peak and then decays back in a much more symmetric fashion. There's a similar observation for YouTube views, where, for example, here you see a very sharp discontinuity and then a decay, or a much more symmetric type of profile. And what is interesting is, if you look at financial markets now, as you know, as I've mentioned, there are big crashes in the financial markets, but actually every day there's a lot of big moves. For example, on the 1 minute time scale, prices of single stocks can change by 4 sigma or more for standard deviations, which must be qualified as a jump. But there are two types of jumps. One type of jumps is due to news. And by definition, if it's a news, then nobody knew about it before. So the activity before the jump is kind of normal and low. And then there's the jump, and the activity, this is not the price, this is the activity. The activity decays back down, much like we saw this number of book sales going back down in the previous example. But in most of the cases, actually, and this is an interesting observation that already suggests that the volatility of financial time series is mostly endogenous, is that in most cases, you cannot identify a precise news associated to a price jump. And it seems that the market is self-exciting itself. And so there's a rise of activity before the jump. The jump is located at this point here, and then a decay of the activity, much like the examples of book sales and YouTube views. So really, again, as I was mentioning at the very beginning of this talk, the motivation is, can we distinguish exogenous and endogenous phenomena? What is the relative role of these two types of phenomena in the volatility of economics as a whole, or financial markets? And can we have models to try to explain how these endogenous phenomena can come about? So what I'm going to review for you today is the Random Field Ising model, which I've called the unifying model. So, of course, probably some of you know well this model, but I'm going to rephrase it and try to highlight the most interesting features of this model that makes it, in my view, a good candidate to try to think about these events that I've talked about, the way, for example, confidence or trust can disappear in a single day, or sometimes in a few minutes, without real causes. So the random field Ising model is initially a kind of toy model for disordered magnets, and it is, as I'm going to remind you in a few slides, a generic model that leads to a transition between individual behavior and collective behavior. And in particular, it captures this very widespread phenomenon of multiple equilibria, of hysteresis, and also of avalanches and discontinuities in what will turn out to be demand curves in my examples. So, of course, it's an Ising model. So we have spins SI that are +1 or -1. Here I denotes an agent. There are n agents in the model. And +1, -1 can mean trust and mistrust on the banking system, buy the stock market or sell the stock market, decide to go voting or abstain. And of course, you can cook up all types of examples, and I'll give other examples like having babies or not having babies, or clapping or not clapping. And so the random field Ising model specifies the following dynamics. The position of the spin, or the orientation of the spin at time t, is the sign of the sum of three terms. The first term, hi, which is the random field in the random field Ising model, this is a static number that goes from -infinity to +infinity, say. It belongs to each agent. It's drawn from a certain distribution, rho of h, and it's, as I said, it's static, so it models the individual propensity to do something or not do something. So let's take the example of clapping. Say, if my HI is large, I have a large propensity to clap, and if HI is large negative, I don't want to clap. The second term, capital H of t, which can be seen as the average of all these HI, but I can define the HI to have zero mean and put all the mean in this capital H term. This is supposed to capture public information. So if we change a little bit the example we're talking about, if we're speaking about buying a product or not buying a product, this H of t can be a measure of the price. So if H of t is large, it means that the price is small, or the quality of the product. You'll see later that another type of data that we analyze is the way cell phones invaded the markets back in the 90s. And if you remember, those of you who are old enough to remember when we had no cell phone, at the beginning, cell phones were expensive, and the quality of sound was pretty low. So H of t was pretty negative because nobody wanted to buy expensive, lousy objects. But then as time progresses, H of t becomes more and more positive, which means that people are more and more enticed to buy a cell phone. And then, of course, the last term, which makes the whole story interesting, is this social pressure term. So sum over j, j being some neighborhood of I, which can be defined on a graph or defined, or maybe a mean field, so everybody talks to everybody else, times the decision of h and j at time t-1. So this is really what makes the random field Ising model interesting, is to be able to capture the effect of these three terms: individual propensity, public information, and social pressure. So let's see what happens in mean field. So when everybody talks to everybody else, which, by the way, is a good model for concert halls, because in concert halls, you hear the sound of what everybody else is doing when they're clapping. So let's take, to make the discussion easy, a case where all the jij's are equal to some unique value j divided by n, where this scaling is needed to have a proper large n limit. And what happens in this model is that there are two phases, depending on whether J is small, meaning weak social pressure, or whether J is large. And maybe the best way to understand what's going on is to imagine my example of cell phones. And so there will be two possibilities, depending on whether J is less than this critical value JC or J is greater than JC. So let's look at the blue line first. Imagine J0, for example, the simplest case where there's no social interaction at all. You don't care what other people are doing. And then as the price of the cell phone decreases, or its technological quality increases, there's more and more people who have an intrinsic propensity, this HI, small hi random field term, that makes them flip from not buying to buying. So on the y-axis, it's the average number of people buying, if you want, or the magnetization in physics terms. So it starts at -1 when everybody is -1, and then it increases. The slope increases as well, reaches a maximum when you reach the maximum of the rho of H, of the distribution of idiosyncratic field. This is easy to show in mean field again, at least if rho of H is a single maxima, so that I'm going to restrict to this simple case. And then the slope decreases again, and you reach 1 for large capital H of t, which means then when the price is, this is the current situation, when the price is low and the technology is very good, then everybody has a cell phone. So the blue line is essentially a reflection of the individual propensities. There's a one-to-one mapping between the blue curve and rho of H. Actually, the blue curve is just the cumulative distribution of idiosyncratic fields. So this is the standard economic situation, if you want, where people decide based on their utility function, and their utility function only depends on the quality and the price of the product, if you want, but not on what other people are doing. And this is more or less correct if J is weak enough. So as J increases, the curve deforms a little bit, distorts a little bit, becomes a little steeper, but qualitatively it doesn't change. But then as you reach this critical point JC, the curve completely changes. It becomes the red dotted line, where at first nobody buys a cell phone, and even if prices are low, people don't buy cell phones because nobody else buys cell phones, which might be imitation, but in this case, it might just also mean that if nobody has a cell phone, then it's useless to have a cell phone yourself. So there's no externalities, if you want. And so the curve here is suppressed. And then it reaches a point where suddenly, without any specific event going on in the world, everybody jumps and buys a cell phone because everybody else jumps in and buys a cell phone. So the curves start being continuous for small j and end up being discontinuous for large j. And of course, what's interesting about this phenomenon is that if you were able to go backwards, then the point where the red curve goes down is not the same place where it went up. So there's a hysteresis cycle that opens up. So this is really interesting in the context of economics, and in particular here I want to cite Keynes, who had understood many of these things back in the 20s or 30s of the last century. But of course, unfortunately, many of these ideas were forgotten. So he said, a conventional valuation, which is established as the outcome of the mass psychology of a large number of ignorant individuals, is liable to change violently as the result of a sudden fluctuation of opinion due to factors which do not really make much difference. So if you want to think about the stock market here, so we might be on the higher branch, and it's a euphoric situation where everybody believes that the stock market is going to go up forever. So everybody buys the stock market, but at the same time, the objective situation of the economy is degrading, and then suddenly, as a result of a sudden fluctuation of opinion due to factors which do not really make much difference, as Keynes would say, there can be a crash. So this is the mean field solution. There are many other things that one can compute. For example, this discontinuity, the height of the jump delta, is 0 in the continuous phase, in the blue phase, because there's no discontinuity. And then as J increases and goes beyond JC, then the gap opens up with the square root. And close to JC, one can observe avalanches. So when one is slightly below JC, the way the system is reacting to one little increase of h of t is through avalanches. One person flips his mind, changes his mind, and by doing so, he's able or she's able to bring together a small assembly of people or a large assembly of people. And actually, this is equivalent to a branching process close to the critical point. And therefore, one has a parallel distribution of avalanche sizes. What is interesting about this random field Ising model has been pointed out by Damen and Setner a long time ago, is that you don't need to be very close to the critical point to be able to observe these critical phenomena like avalanches and critical exponents. And this is interesting because it means that maybe the existence of a critical point in the random field Ising model is relevant for real situations. And this is what we try to test on some data. So the idea of the analysis, let me try not to go into much details, but essentially what we try to do is to look at different data sets, birth rates, cell phones, as I've mentioned earlier, and clapping data. And if you take M of t, you remember M of t is the participation, if you want, or the total demand. So the derivative of this curve is clearly having a maximum around this point. And so you can study the derivative of this curve as a function of time in these examples. And the prediction of the proximity of a critical point of the random field Ising model type is that there's an anomalous scaling between the width of this curve, the width of the MDT, and its height. In general, if you take the derivative of an object that goes from -1 to 1, the width and the height scale inversely proportional. So there's a trivial scaling between W, the width, and height, which is 1 over W. But in the proximity of this critical point, there's an anomalous scaling where the height scales as W to the -2/3 in mean field. And this is what I'm trying to show here. The blue line is the trivial slope, and the red line is the slope -2/3. And of course, there's not a lot of points, and I'm not going to claim that this is very convincing, but at least it's not completely absurd to think that birth rates are affected by what your neighbors are doing, what your friends are doing, and so on, and cell phones as well. And it's not completely crazy to see an alignment of these curves along the slope predicted by the random field Ising model. And this is the case for applauses at the end of concert halls, of concerts in concert halls. And what we've observed is that indeed there's a wide variety of ends of clapping. And if you do this analysis, there seems to be some relation that follows. I mean, actually, the fit through the points gives a slope of -0.64, which is not that far from -2/3. In any case, it's I think it's more toy model, a metaphor of these social phenomena, rather than a proof that random field Ising model applies in these cases. So let me tell you the same story, but with different close, which I think is interesting because it opens the discussion in the direction of a more general aspect, which is the aspect of what I've called fragile optimization, and which is related to this fragile fracture that I've talked about earlier. So this is the so-called restaurant problem. So it's illustrated here by these two restaurants or cafes facing each other in Venezia. Of course, I mean, I've cheated because the picture is not taken the same day. Obviously, one is during Aqua Alta, and the other one is I don't know, during summer or something. But anyway, what this is supposed to illustrate is that very often you go to a square and there's a restaurant that's full and another one that's completely empty. And then you come back the next day and it's the other way around. And there's no real reason except that as soon as some people sit in the first restaurant, then others who are tourists and who don't know much think that the first one who sat down have some information, and therefore they heed the implicit advice of these first tenants. So this is the same model, but I've just changed a little bit the notations. So what I've called capital H before, I'm going to call it quality of the food minus price of the menu, PT, small p. HI is this idiosyncratic field that people in the field of consumption call willingness to pay. J is the taste for well-attended restaurants, that is this social pressure term. And phi is the equivalent of what I've called M before. Instead of being between -1 and 1, it's going to be between 0 and 1, and it's the restaurant's filling rate. And so within the context of this mean field, random field Ising model, one has an equation that kind of implicitly mentioned before, but where the filling rate phi is equal to the cumulative distribution. I mean, the probability of exceedance of idiosyncratic willingness to pay being larger than price minus some social term. So what it means is that in this context, the fact that the restaurant is well attended is like having a lower price. It's more attractive, even if the price is high, just because there are other people there. So let's look at this model, which again is the same model disguised in a slightly different way, but in the precise context where rho of h, this distribution of idiosyncratic fields or idiosyncratic willingness to pay, is an exponential distribution with values for only on the positive axis. So there's nobody willing to pay. I mean, willing to pay negative prices is irrelevant in this model. So I'm just taking rho of h to be a single decaying exponential. There are very little people wanting to pay extremely high prices, and then it reaches a maximum for h equals 0. So the explicit equation, self-consistent equation for phi is written here. And you can draw the solutions depending on various parameters. So for example, here I've shown what happens if this social pressure is small. So the relevant parameters are gamma j and gamma p, where gamma is the inverse width of rho of h. And so what you see, if, again, social pressure is low enough, then there's only one solution to this equation for all prices. And what you find is that as you increase prices, as the restaurant owner increases their menu cost prices, then at the beginning, the restaurant remains full because of social pressure. Because it's a popular restaurant, people accept to pay higher prices for a while. And then when prices exceed a certain threshold, then attendance starts to decay down. And of course, for large prices, attendance goes to 0. So this is the classical case, if you want. Maybe there's a little phase here that's not completely trivial from the standard economics point of view, where attendance doesn't depend on price, actually, but then attendance goes down with prices. But now what happens if social pressure is high? is the opening of a hysteresis cycle. So now you can increase your price quite a lot before losing clients because of social pressure. But by the same token, what happens is now, instead of being a kind of continuous decay of attendance, it comes out of the blue that the attendance drop discontinuously to a low value, which in this case is 1/2 gamma j. And then as you would start continue increasing prices, then attendance would still go down lower. But then, having realized his mistake or her mistake, the restaurant owner tries to backpedal and lowers prices again. But unfortunately, in this context, the fact that you've lost attendance, you've lost tenants, means that the restaurant is less attractive. And so instead of going back up at the point where it went down, you actually have to lower your price quite a lot more before people accept to join back the restaurant. And so you see here that what is interesting is that in this case, there's no precursor in this model. There's no precursor to the jump. And what all is interesting, and that I'm going to speak about now, is the fact that the optimal point for the owner of the restaurant is clearly this point, because this is the point where attendance is maximum and prices is high. And so the profit of the restaurant owner is maximized. But it's also exactly the point where it's most dangerous to sit, right? And of course, in a model, it's possible to compute where this point is, but in practice, it's impossible, first of all, because the model is a model and it's not describing faithfully reality. But even if the model was describing reality, you would need to know the value of the parameters, which would entail some measurement. These value parameters might evolve with time, and so it's actually impossible to know where this point is. And missing the point by a small amount can lead to completely different outcomes. So this is what I like to call a kind of cliff edge optimization, which is that optimization drives you in this model exactly to the point of instability. So this is in a way illustrating the fact that optimization can lead to fragility, because by pursuing the objective of optimizing the system, people are sometimes inadvertently pushing it to the limit where it becomes unstable. And so this is a very simple example where this happens, but there are other much more complex or much more sophisticated examples where exactly the same phenomenon occurs. That is, trying to optimize the system leads to the proximity of a critical point or a failure point. And so optimization also often comes hand in hand with lack of resilience. And this is something that has been empirically observed in the context of rail networks, where in order to optimize the rail network, so a rail networks, for a train to depart, you need the train to be there, you need the machine to be there, you need the driver of the train to be there, but you also need the attendant to be there. And so there are various things that must happen simultaneously for the train to leave on time. And of course, if one train arrives late, you have to account for the fact that this train has arrived late, or the train driver has arrived late. And so in the timetables, you have to allow for delay buffers that allow the next train to leave on time, even if some delays have occurred before that point. And in simple models of this problem, what you find is exactly the same thing. That is, of course, creating time buffers is costly because you're not able to run as many trains as you would like. You need more train drivers and so on. So delay buffers or ways to optimize the system are costly. So you're going to try to reduce this thing. And as you reduce these delay buffers, you drive the system close to criticality. And so this is a paper that we wrote with Deb Panja and others in Utrecht, and the paper is called Timeliness Criticality. By the way, you see, is I've said that in this case, there's no precursor, and it's really very similar to the brittle fracture example that I've given at the beginning. So all this was, in a sense, zero temperature, where each spin aligns to the total field, to the sum of the three components of the field, the idiosyncratic component, the external component, and the social component, or the interaction component. One can extend these analyses to what in physics we would call non-zero temperature, which also exists as a counterpart in decision theory or choice theory. So people have modeled the decision to make a choice over other possibilities in a way very similar to Boltzmann-Waite. This is called choice theory, and I can give references, of course, if you want. And so beta, the inverse temperature in physics, is, you can think of that as the amount of irrationality. That is, the best choice would be to be at zero temperature, that is, to take the decision that minimizes energy. But for various reasons, people can, be sloppy or not be fully aware of their interests or whatever reason. And this is modeled by a non-zero temperature. And at high temperature, people would make random choices independently of their true interest. So that's what I've said earlier. And the only thing to remember in this case is that there's a phase diagram which is now in the for fixed social pressure. Sigma is the variance of rho of H, the dispersion of propensities, and T is 1/beta. And so there's a phase diagram where there's a line where above which the curve is smooth, the bond curve is smooth, the blue phase that I've talked about, and below which there are discontinuities. So it is not that the whole phenomenology disappears when you add a little bit of randomness in the system. It remains true that there are two phases, which is important for thinking that this framework is robust and generic. As you know, non-zero temperature also means that hysteresis is not going to be there forever. There's going to be a relaxation time, which can be very large and is related to the presence of an energy barrier between the two possible stable solutions. So here I'm referring to, so let's go back to this graph here. So the blue line corresponds to one solution, and the red line corresponds to three solutions for each value of H, one unstable and two stable ones. And you can represent these solutions as the minima of some potential. And so if you're stuck in a bad minimum and the system actually would like to transition to another minimum, there's a barrier to cross, and one can compute the time to cross this barrier. And of course, when the system is in mean field and everybody's interacting with everybody else, then the size of the barrier is proportional to n, which means that for large n, hysteresis is there forever, but for n's finite, or for models that had finite range interactions, there's a relaxation time that can be very large, but that can also be reduced by various policy tools. So if you're able to make people coordinate, or if you're able to nucleate some good behavior somewhere, of course, as we know from physics, this allows the barrier to be overcome. But I won't go too much into these possible developments. I'd rather give you two more incarnations of this idea of social pressure and the role it can have in socioeconomic contexts. One is to adapt. So the random field Ising model is, of course, something that physicists like a lot to think about, but economists rather want to have these ideas embedded in a more classical way of thinking. And so what we've done here, and that I'm going to speak very quickly about, because it's, as you're going to recognize, is the same kind of ideas, is to embed these ideas of social pressure within more classical models, equilibrium models that economists like to talk about. So as you probably have heard of somewhere in or sometimes in your life, economists think about agents optimizing utility functions. And so this is a typical utility functions that depends on consumption and number of hours worked. So households maximize the trade-off between consumptions and labor. So this is a typical utility function. The log of consumption with a positive coefficient g, which is usually taken to be time independent, and then a negative contribution coming from the amount of labor produced by households, and based on the fact that, of course, working gives you a wage and allows you to consume, there's an optimization that you can devise. So here we can follow the whole route that rational economists like, even if this is not necessarily my cup of tea, but doesn't matter. At this point, just as a kind of proof of concept, let's now imagine that this coefficient G, this propensity to consume, instead of being a constant, depends on various factors, and in particular depends on confidence. Could also depend on inflation and other factors, but let's assume that indeed households, we know that this is true, that households consume if they're confident about the future, if they're confident about keeping their jobs and so on, and stop consuming when confidence go down. So let's make the hypothesis of a kind of self-fulfilling confidence loop, where confidence is actually measured from realized consumption at the last time step. So it means that people look around or people read the news and see that there's been a drop of consumption, and therefore adapt their propensity to consume to this new state of affairs. So here it's a standard construction. The consumption would be something between -1 and +1, and it tends to be negative if the consumption of the past time step was below some threshold C0, and tends to be positive otherwise. And this coefficient theta c is the width of the transition region between no confidence and high confidence, or low confidence and high confidence. So you take this this form of G. I mean, G depends smoothly on C. You put it in there. You turn the crank of the usual utility maximizing framework. And what you find in the end is that the total output of this economy depends on C0. So everything else being the same. So remember, C0 is this threshold. If C0 is low, it means that it's very easy for consumption to be above C0. And so confidence will play a minor role. It's always going to be high. And what you see is total output fluctuates about its equilibrium level. The fluctuations are due to shocks, to external shocks. So this is, again, the economics standard framework is to assume that all the fluctuations are driven by exogenous shocks. But if you compute the volatility around the equilibrium, you already see that as soon as there's a coupling between G and C, the volatility, the standard deviation of these fluctuations is slightly higher than what it would be without feedback. So without feedback, you would have fluctuations that reflect entirely exogenous shocks. But in the presence of this feedback loop, this confidence feedback loop, there's already in this phase a slight increase, what people call excess volatility, compared to true shocks. And then as you increase C0, which means that the possibility of going below C0 increases, and therefore the possibility of entering a phase where people stop consuming because other people stop consuming, as C0 increases, you see that there are spikes below this red line that represents in the previous example that would represent this unstable point here. And then so the bottom graphs represent the distribution of output of the economy. So here you see it's Gaussian. Here you see there's a little tail starting to grow, and then there can be, as C0 increases more, the possibility of bistability with long phases where the economy is clearly in a crisis phase, where consumption is low just because confidence is low, and it can only pick up because of positive shocks that reestablishes the high output state of the world. So I had other things to talk about, but I see that I'm reaching the end of the 50 minutes, so maybe I'm going to stop, just showing very quickly that, of course, everything that I talked about was non-spatial. Was a mean field model that I talked about in the random field Ising model. Economics model are, based on so-called representative agent, where there's no geometry, there's no space, and so on. But actually, one knows that social effects are also geographic. They propagate in time and in space. And this is an example of how the riots in the Paris suburbs propagated around Paris in 2005. This is the paper that I haven't had time to speak about, Verestiki, Nadal, et al., if you're interested. And this is our own study of the participation rate in the European elections. So this graph is for 2004, but we've looked at other elections. And what's interesting is that clearly the pattern of these, so blue means low turnout, and red means high turnout. And what you see is that it's not at all random. And actually, the correlation of this participation field, of this propensity field to go voting, has a logarithmic behavior as a function of distance. And we've proposed a kind of Edwards-Wilkinson random diffusion equation to try to make sense of these patterns. But I won't have time to speak about this. So, as a conclusion of this first part, I'd like to recall what Barack Obama said when he arrived in January 2009 after the 2008 crisis. And what was surprising is that nothing had happened. Nothing concrete had happened. There was no hurricane, no war, no major disruption, physical disruption, and still there was this macroeconomic crisis. And so he was puzzled by this and said, our workers are no less productive than when this crisis began. Our minds are no less inventive. Our goods and services no less needed than what they were last week. And still the world had changed in October 2008. So this really is what I've talked about today. I mean, this first lecture was about how to make sense of these discontinuities without causes that can arise because of the proximity of an unstable point that is lurking somewhere. So I'll probably stop here.
Thank you, Jean-Philippe. According to the schedule, we have a little break now. I don't know if you need some break, drinking something, or one can perhaps ask.
Yeah, I'll probably take 2-minute break, but I can answer questions now, of course.
Okay, let us have some questions if there are some in the audience. Please.
Yeah, sure. This is Joe here from UK. Thank you very much for the good presentation. I hope you can hear me well.
Yes, I can.
Okay, good. Thank you. Very interesting presentation there. So I work with time series in the industry. And what you have touched on there is something that we struggle with when you're trying to model time series. Sometimes we call these geopolitical trends, or we call it many different names. but or geotrends or news or activities as you explained in here. My question is, how do you identify an associated activity if you are following a certain time series, or if you're following the trend of a specified time series? For example, if you're following, say, the price of one specific share, how do you associate an activity or a trend with that to model these discontinuities? Thank you.
Yes, well, it depends on the type of data that you have at your disposal. But in the examples, sorry, you still see my screen, right?
Yes.
So in this particular example here, what one has is either only prices, or you can have prices and transactions. I mean, each transaction is recorded, but you can also have the full limit order book. So everything that happens in the financial market. So it's really depending on the granularity or the complexity of the database, you can do different things. So here, what we have is just 1 minute time price changes. And in this case, what you can do is so what we have done very concretely is to measure a variance or standard deviation of the price changes in the recent past, in the few hours before zero, if you want. And then the price jumps. I mean, the price changes all the time, but if the amplitude of the price jump is larger than 4 sigma, sigma being the local sigma, the sigma of the last few hours, it's even more complex because actually in financial markets, there's a intraday seasonality. I mean, volatility tends to be high at the beginning of the day, then goes low and then high again at the end of the day. So you should deseasonalize to get rid of this profile. Having deseasonalized, you can also have a local, high volatility because there's something going on. So you should rescale by this local volatility. And then there's a threshold that you can fix either by hand saying, I'm going to look at 4 sigma, 8 sigma, or you want to have some more sophisticated statistical threshold that tells you whether or not you should expect these events to happen in the Gaussian world, for example. So the threshold might be subject to debate, but essentially, this is how we identify these jumps as events that exceed some threshold.
Okay, thank you. I think we should have now a 2 minutes break so everyone can relax a little bit, and then we expect you back sharp
Okay.
at